Welcome to our computational complexity theory learning material. First, let me explain the title a bit. Our computers do computations. We, programmers, developers, write algorithms to solve certain computational problems. We would like to investigate how the complexity of different algorithms relates to each other. Which one is faster, which one uses less memory. We will do similar investigations with the computational problems themselves. Here will the underlying theory help us. Of course, the computational complexity theory uses some mathematical formalism, but don't be scared, it won't be difficult, I guarantee. Let me first emphasize how important to do theoretical investigations on computations by telling you a story. In the 1950s or 60s, when the first computers were ready to be used in practice, everyone was very optimistic. Everyone thought that any computational problem could be solved by computers until the 70s, when two scientists, Stephen Cook and Richard Karp, showed that there indeed existed certain computational problems which were intractable for computers. There is no algorithmic way to solve them in reasonable time. To prove this, they used a theoretical concept, the so-called NP completeness, about which we will learn later on. By utilizing the concept of NP completeness, we can prove that certain problems are intractable. This is an important knowledge for us, programmers too. Let us suppose that you are going to be employed as a programmer at a company, and one day you get a programming task. You have to develop a planning software for a delivery company. Every morning, your software will be used to generate a schedule for a truck driver. It tells him or her where to deliver first, where to deliver next, and so on. The truck must not deliver the same destination twice, and must return to the initial location at the end of the day. This is a well-known computational problem called the traveling salesman problem. This problem can be derived from a well-known graph problem, the Hamilton path problem. What is interesting here is that the Hamilton path problem has been proved to be NP complete. Recall this concept by Cook and Karp. Which basically means that this problem is intractable in an algorithmic way. It cannot be solved fast, at least for a certain number of destinations. Your algorithm might work for 50, 100 destinations, but if the company starts to flourish and our salesman has to visit, let's say, 150 destinations, your algorithm might slow down. It will drastically slow down sooner or later, and this is guaranteed. Let me tell you another example. Let us suppose that you are going to get a PhD and work in a DNA laboratory. You will need to write a program that receives as an input a DNA sequence and tries to build the same sequence from other building blocks. If you have learned about computational complexity theory, and obviously you have, then you will know that this computational problem can be derived from a famous mathematical problem called the post-correspondence problem, which is not only intractable, but indecidable. This means that there inevitably exist cases or inputs such that your software will stuck in an infinite loop. It is not guaranteed that your program stops. And the theory tells us that the stopping problem cannot be avoided in this case. Okay, I hope I was able to demonstrate why computational complexity theory will be used will be used for you in practice as well. The learning material starts with investigating certain types of computational complexity of algorithms. We are going to deal with only two types of complexity. First of all, time complexity, which is about investigating how fast or in how many steps an algorithm runs. Second, space complexity, which tells us about how much memory an algorithm uses. In the subsequent sections, you are going to look into significant computational problems, the search problem and the sorting problem. For these two problems, we will do investigations on several well-known algorithms. We will determine their complexity and we'll compare them against each other. Which algorithm is faster? Which algorithm saves more memory? This will be a very practical stuff. Later, as the learning material progresses, the objective becomes to classify computational problems into complexity classes. We will create big complexity classes. There will be such a complexity class to which a computational problem is advantageous to belong, meaning that the problem can be solved fast. There will be such a class which consists of intractable problems, meaning that they cannot be solved in reasonable time. There will be classes which indicate memory efficiency. There will be other ones which indicate wasting memory, and so on. The point is that we are going to draw a map of complexity classes and locate well-known computational problems on this map. Well, on behalf of the creators of this learning material, I wish you success and enjoyment for discovering the universe of computational complexity. We will meet again throughout the subsequent sections, and thank you for your attention.